So, last time we saw how we can calculate the nonlinear impedance for a reaction, two step reaction with one adsorbed intermediate, right. At that time we saw that when you apply a sinusoidal potential, it takes some time for the response to stabilize. That means, when we apply the sinusoidal potential, the current and the fractional surface coverage of the intermediate species, both of them, they do not immediately give you a steady periodic result. Instead, they will have a drift or a change in the value, average value. It will go, for example, like this, it may go like this, we have seen one example. It will change, and then after some time it will give steady periodic result. The average value of that fractional surface coverage or the average value of the current, they will be different than the initial steady state value. Okay. So, what I want to discuss today is how long should we wait, can we estimate it, or do we have any idea on how it depends on the parameters such as the frequency or the amplitude. Okay. Second, the average surface coverage, it settles at a value which is different from the steady state value. So, when we apply only EDC, we get a theta SS. When we apply EDC plus EAC, the theta has a sinusoidal oscillation after stabilization. That average value of the theta is not theta SS. Okay. We call it as theta average, just to differentiate that from theta SS. And where will it settle? How does it depend on the amplitude? How does it depend on the frequency? Third, what if I do not wait long enough? In the simulations I have an idea, okay. I can calculate and then say you wait for this much time, it will give you steady periodic result. In the experiment, we usually take a system, run the experiment, we validate with KKT. If you do not wait for sufficient time before we take the data, then the spectra we get is going to be different than the one we would get under steady periodic result. Okay. So, what happens when we get this? Can we identify it? Can we identify and say we are taking data when it is not settled yet, when the current periodic oscillations have not settled yet? Next, without going through this entire simulation process, can we estimate the value of at least few parameters? One is charge transfer resistance under nonlinear conditions, another is polarization resistance under nonlinear conditions, without solving the ordinary differential equation. First, just to refresh your memory, for a particular set of parameters and frequency and amplitude, initially it oscillates, but the average value is not independent of time, it changes with time. After some time, when I go to, in this case, 0.09 to 0.1 second, that is 90 to 100 milliseconds, it is more or less stable. Okay. So, mean theta or theta average after stabilization, and that is different from the initial value. Initial value is somewhere between 0.82 to 0.84, and the final value in this case, this is close to 0.91 or so. So, what else can we learn from this? What I am going to describe to you is basically an empirical evidence. That is, we have done simulation for a variety of parameters, we have done simulations for a variety of mechanisms. I am illustrating one set of parameters for one mechanism, but I would ask you to trust that it works similarly for other cases also. Okay. One, how long do we have to wait to get steady periodic results? So, in this case one can say 0.05 is good enough, maybe 0.04. What is the value of theta average, and how does the theta AC, that is the amplitude here, how does that vary, and how do they depend on the two parameters that we control, EAC0 and F. Of course, it also depends on the reaction, it depends on the DC potential, but at a given DC potential for a given reaction system. we are going to vary frequency and the perturbation amplitude. So, here there are couple of examples, one for the same system, same DC potential, same AC perturbation amplitude. I have shown one example with 1 kilohertz, another example with 100 hertz. Both cases you can see 0.05, maybe 0.03, it would settle. That is the time it requires for giving a steady periodic oscillation, that is not strongly dependent on the frequency. So, what it means is, if I apply sinusoidal potential and ask the instrument to wait for some time and then acquire data, that will be correct. If I ask it to give few cycles, 5 cycles and then take data, that will not be correct. At low frequencies it would wait unnecessarily long time, at high frequencies it will not wait long enough. So, it should not be number of cycles that one needs to wait, it actually is the time duration that one needs to wait before it goes to steady periodic result. Okay. So, sometimes the equipment will give you, or the software will give you an option, wait for certain time and then take data, or wait for certain number of cycles and then take data. It is better to choose the wait for some time, and then of course, assume that we are giving enough time. Okay. If you give too much time, then you are wasting time, we do not have to wait for that long to take the data. If you give too little, then basically our results will not be in the steady periodic regime. Okay. But if you give for certain number of cycles, that will be inappropriate. So, in this case system stabilizes to steady periodic results after certain time, approximately 50 milliseconds, and wait time is basically independent of frequency. The average value that we get is more or less same. If you just view it and then have to eyeball it, you would say it is somewhere at 0.915 is the theta average. So, for a given AC perturbation amplitude, if you change the frequency, it does not change the average value of theta, it does not change the time it takes for stabilization. However, notice that the amplitude here is half of the peak to peak value, and the amplitude here is significantly smaller. The amplitude here, it goes, for example, I can say it goes from 0.89 to 0.93 very roughly. Here it stays between 0.91 to 92, peak to peak value is much smaller compared to this. So, lower frequencies the amplitude is more, that is to say the amplitude of theta, that is theta AC 0. If I write it as theta AC 0 sin omega t, assuming it is a sinusoidal wave, or assuming I can fit it to a sinusoidal wave, right, that decreases as expected. So, basically what it means is, if I give a large potential, if I give high frequency, then the fractional surface coverage cannot keep up with the changes in potential. If I give low frequency potential change, low frequency sinusoidal wave, then the rate constant changes slowly, the fractional surface coverage can keep up with that. So, essentially theta average, time it requires for settling, these are independent of frequency, theta AC 0 decreases with frequency. So, higher frequency it will be smaller amplitude. Of course, this is on one case, but it basically works similarly for pretty much all the cases. Now, I would like you to look at this. We can write theta as theta average plus theta AC, where AC does not necessarily mean it is one sinusoidal wave, it could be written in Fourier series, with theta 1 sin omega t, theta 2 sin 2 omega t, etcetera. And approximately I can write it as d theta by d e EAC 0 sin omega t, provided the higher harmonics are negligible. We have done this in linearization, and when we have used this linearization, we have derived that d theta by d e can be written as, for this particular mechanism, can be written as b 1 k 1 d c 1 minus theta s s divided by k 1 d c plus k 2 plus j omega gamma. What this means is, if I increase the omega, d theta by d e, the magnitude of that will decrease, that is increasing frequency will decrease d theta by d e, and that is actually going into the coefficient of this sin omega t. This essentially is, at least under linear conditions, you can see theta a c is equal to theta 1 sin omega t, and theta a c 0 is going to be equal to d theta by d e E a c 0 for a given perturbation amplitude. If I change frequency, d theta by d e will decrease. So, essentially at high frequencies, theta oscillations cannot keep up with the potential oscillations. Now, what happens if we change the EAC 0 amplitude of perturbation? Going from 100 millivolts to 200 millivolts, we maintain the same frequency of 100 hertz. First thing to notice, this takes certain time to stabilize. This stabilizes much earlier. Okay. Second, in this example, this settles at somewhere at around 0.91, this settles somewhere maybe 0.96, 97 in that region. Third, the oscillations, it goes from maybe 0.94 to almost 1, 94 to let us say 99. This goes from 0.89 to 0.93. So, about 0.04 units here, this is 0.5 units, maybe a little more. So, the amplitude increases with EAC 0. Okay. This works generally, may not be always true, it may saturate at some level. If average value of theta is close to 1, then theta cannot exceed 1 anyway. So, by increasing the amplitude, one may not expect that theta AC 0 would always increase. Okay. It would increase, it might saturate under certain conditions, but in general I expect that if I give a larger amplitude sinusoidal perturbation in potential, I would get a larger amplitude in theta oscillations. Stabilization time clearly decreases. Okay. When I go from 100 millivolts to 200 millivolts perturbation, if I go from 10 millivolts to 20 millivolts or 10 millivolts to 5 millivolts, it may not change that much. That means, okay, coming back here, the average value depends on the applied AC 0. In this case, its average is around 0.91, this is about 0.96. It does not automatically mean that it will always increase. We have seen examples where it can decrease, some examples where it will increase. So, it basically depends on EAC 0, but we can't say it is monotonic change. This is just another example where we maintain the same potential, same amplitude, but change the frequency. So, when we apply 200 millivolts and 100 hertz, it stabilizes very early. When we apply 200 millivolts on 1 kilohertz, again it stabilizes very early. Probably it is little easier to find the value here on what value it stabilizes at, but pretty much the time it takes to stabilize is independent of the frequency. It does depend on the perturbation amplitude. So, this is at various values. Okay. 150 millivolts 1 kilohertz, 100 millivolts 1 kilohertz, 50 millivolts 1 kilohertz, 20 millivolts. So, the same frequency, but decreasing values of perturbation amplitude. So, if you notice, it stabilizes at let us say 0.02 seconds, this may be little more than that, this is little more close to 0.04, but then it is 0.04. Now, look at this, at 1 millivolt this theta average actually decreases, that is it is lower than theta SS. At 10 millivolts it is higher, that means at some intermediate value maybe 5 millivolt, 2 millivolt, it would be more or less same as theta SS. That is one point, we will come to that. Other thing is the time it requires for stabilization does not keep increasing when I decrease the amplitude. So, when I go from 150 to 100, it increases a little, it stabilizes early, it stabilizes a little late here. When I go from 100 to 50 millivolts, it stabilizes little later, 50 to 20 not much later, 20 to 10 more or less at the same time, 10 to 1 more or less at the same time. So, it does not just keep increasing when I go to lower and lower potential. When I go to higher and higher amplitude, it does decrease, become shorter, but when I go to lower potential, it does not keep increasing continuously, it increases and saturates at some level. So, summary is wait time, if I just draw it qualitatively, at large amplitude perturbation it is lower, at small amplitude perturbation it is more or less a constant. Of course, this will depend on the kinetic parameters as well as the DC potential at which we are acquiring the data. For a given set of kinetic parameters and given EDC, this is how would you expect to see. Next question. Okay, we know that theta average is different compared to theta steady state. Without doing this simulation, without solving it, can I estimate the value? We can estimate it provided this is kinetics limited, that is solution resistance is negligible, mass transfer is rapid, and our assumption that this reaction here m going to m plus adsorbed and m plus adsorbed going to m solution is limited by kinetics. Under that condition we can estimate it. It is an empirical formula, but it seems to work. Okay. Now, to summarize what you have seen so far, it takes some time to stabilize and give steady periodic results, and the time it takes to stabilize or what we call as wait time in the simulation, we have to wait until that time and then only start taking data. That is independent of frequency and it depends on EAC 0, when EAC 0 is large. When EAC 0 is small, it is more or less constant, and at lower frequencies the theta oscillations exhibit larger amplitude, that is theta AC 0 becomes larger at lower frequencies. And we notice that the mean value of the surface coverage is different from the initial value, that is theta steady state value. And by the way, although we are not showing it here, even when AC perturbation amplitude is very small, even when you can approximate and say e power EAC is roughly 1 plus EAC, we can solve this case analytically and we can still show that theta average there will be different from theta SS. So, it is not happening just because the AC perturbation amplitude is large, even when it is small it will be different, and that is because the theta is given by the differential equation, it is not an algebraic equation. So, when we write the theta under small amplitude perturbation can be written as theta steady state plus d theta by dE into EAC, that is actually only an approximation for this as well as this. It is not exact for even for the average value, even when EAC 0 is small. Now, the average value of theta is independent of the applied frequency, and theta AC depends on theta average depends on EAC 0, but it is not monotonic, at least that is what you have seen in this example, and in general that is true. The amplitude theta AC 0 will decrease with frequency, okay, and it tends to increase with EAC 0, but that is not always true. Now, when we actually do the simulation versus when you do the experiments, there are some differences. When we do the simulation, it is actually very time consuming for the high frequency simulations. Okay. When you do experiments at high frequency, they are fast, meaning if I ask the instrument to take data at 10 kilohertz, in 1 second it can complete 10,000 cycles. That is good enough to take a average value and good enough to get a good signal to noise ratio. So, if I ask it to wait for 2 seconds, it waits for 2 seconds and then takes data for maybe another 100 milliseconds, and that is usually good quality data. When we do the simulations, what happens is the following. In the simulations, it oscillates very fast, right. Within 1 millisecond at 10 kilohertz, it means 10 cycles are completed, okay. And we have to give certain accuracy, certain tolerance. This takes actually quite some time in the computer to complete this. Okay. So, basically what it means is, in the numerical simulation, to complete a wait time of 1 second or 1 millisecond or few milliseconds, especially at very high frequencies, it can take long time for the computer to complete this, and then acquiring data under steady periodic conditions for few cycles, maybe 10 cycles, 100 cycles in the high frequency regime. When you actually look at the computation time, high frequency data, it takes longer time in the computer to complete, and if we say I want to perform simulations at 1 millihertz, wait for 1 cycle, that is waiting for 1000 seconds, and then do simulation for 1 more cycle, it would actually take few seconds to do this. And in the experiment, of course, if we say I want to complete a 1 millihertz cycle, it will take 1000 seconds for that cycle, even without any wait time. So, there is some difference between simulating low frequency data and actually doing experiments at low frequencies, and likewise simulating high frequency data and doing experiments at high frequencies. Okay. We take certain shortcuts in the simulations. So, I want to just describe that to you. We do not want to wait for a long time, especially at high frequencies, and still get good quality data. So, we take a shortcut, we want to wait for less time and still minimize the error. Okay. So, if you remember, theta values would start here under steady state condition. When we apply AC perturbation, it is going to drift like this and then settle, or like this and settle. Now, if I know the value where it is going to settle, and if I give that as initial value, then if I give it very accurately, then I do not need to wait at all. It would give you steady periodic result from the beginning itself. If I give it close enough, then after a few cycles it will settle, or even if it is drifting, when I take data for few cycles and do Fourier transform, the results will be accurate. So, there is an advantage in knowing, especially in simulations, in knowing what is the value of theta average without actually solving the ODE with application of sinusoidal potential. And after waiting for some time, even if I take only 1 cycle, the steady periodic results, that is sufficient to get impedance value. But if I take it for few cycles, then if there is a slight drift, that can be taken care of. That means I will get reasonably accurate results even if there is a slight drift. So, how do we predict the value of theta average? I will come to that a little later. Okay. What happens if we take impedance data before the current oscillations have stabilized, before we get steady periodic results? So, I have done the following. I have taken two amplitudes, 1 millivolt and 100 millivolt. In both cases, I have waited for 50 milliseconds and then taken further data, taken the current, done the FFT and then calculated the impedance. Other case, what I have done is apply sinusoidal potential, the response may be still not stabilized, it may be going like this or going like this, does not matter. I take the first cycle, basically I do not wait at all, I just apply one sinusoidal perturbation, look at the resulting current and then take the FFT and then take the ratio of potential to current. So, I would call 0 second as unstable. Unstable does not mean the system is unstable, it just has not settled yet. We can call it unstable, we can call it sometimes drifting, meaning the current is, the average current is changing, but that is changing because we are applying sinusoidal potential, and if we wait for long enough time it will give steady periodic result. If we stop applying the sinusoidal potential, it will again drift and come back to the original theta SS. I would leave that as exercise for you. If you look at 1 millivolt data, 1 millivolt here is the perturbation amplitude. High frequencies, there is pretty much no difference. The line here represents the drifting condition and the points here represent the stable steady periodic result. If you look at low frequencies, again it is pretty much the same. If you look at intermediate frequencies, there is a difference, not very different, but there is slight difference. And of course, these are simulated data, so there is no noise. If you take real life data with some noise, you may not be able to see clear difference between the two in this particular case. Look at 100 millivolt. Very high frequencies, they are the same, low frequencies they are the same, at mid frequencies there is a huge difference. Now, I also want you to compare 1 millivolt data under stable condition and 100 millivolt data under stable conditions, that is the green color circles and the red color squares. Although you have to compare two different plots, you can see that they are more or less the same. There is some difference, slight difference, but not very much. There is some difference in this region. Now, what that means is, if I take data without weighting at 1 millivolt and if I take data without weighting at 100 millivolt, I will get clearly two different sets of data. One of them will be KKT compliant, more or less. It is not going to be exactly compliant, but more or less compliant. This is definitely not going to be compliant, but it is not because this is taken at 100 millivolts, it is because we are taking at a condition where it is still drifting. So, the data is not KKT compliant, but we would just look at this data and look at this data, and if we did not know that, if we did not realize that we have not weighted and that can cause a problem, we would just say that this data is at 100 millivolt and it is not KKT compliant. Whereas, if I take the data which is acquired after stabilization in 1 and 10 millivolt or 1 and 100 millivolt case, both of them might turn out to be KKT compliant. So, this may be one example where KKT is not able to identify the nonlinearity. So, in summary, at small amplitude there is some difference at mid frequencies. With large value of EAC 0, there is significantly larger difference, especially at the mid frequencies. So, the reason is this: at high frequencies most of the current goes through the double layer capacitor. So, if you remember, this is a pictorial representation, this is the double layer capacitor and this is the Faradaic process. But high frequencies you get an impedance which basically is negligible for capacitance. So, most of the current will go through this. This would offer certain resistance, this offers no resistance. So, everything goes through that. So, in that case it does not matter, the current going through the Faradaic impedance is very small. So, total current is pretty much dominated by double layer capacitance. At low frequencies what happens is all the current pretty much goes through the Faradaic impedance, but if you go to 1 millihertz, the response is unstable only for the first 50 millihertz, I am sorry 50 millisecond, and this is going to take 1000 seconds So, pretty much the entire response is in the stable regime, only a small fraction of it is in the drifting region. So, again the response is not going to be very different whether it wait long enough or it do not wait. So, essentially at high frequencies current going via CDL decides the impedance, and at low frequencies stable results come in initial part of the cycle itself. So, I am not showing it here, but spectra acquired without stabilization will not be KKT compliant. So, if you take data and if it is not KKT compliant, one thing you should try is see if the amplitude is small enough. Another thing you should try is see if the data can be acquired after waiting for some time meaning 1 second, 2 seconds. Next, can we estimate the value of theta average? So, this will require some mathematics, follow me with patience. If you look at the mass balance equation, we would write it as gamma d theta by dt as k1 1 minus theta minus k2 theta. So, it comes with the parenthesis, and the k1 I can write it as k1 dc e power b1 EAC and expand it as EAC 0 sin omega t. 1 minus theta of course remains as it is, and k2 is a constant, so we do not expand it. This equation I can rearrange and write as d theta by dt plus p theta equal to q, where p is a function of time, q is a function of time. And after rearranging I would get p as the expression given here. So, I would get k1 dc b1 EAC 0 sin omega t plus k2 all divided by gamma, and for the terms that are without theta remaining on the right side, it is just going to be k1 dc b1 EAC 0 sin omega t divided by gamma. And for this type of differential equation we can calculate what is known as integrating factor, and we would write that as e power p dt multiplied by theta, and we can show that d by dt of this can be rearranged in this form. And the solution for this differential equation we can write as theta equal to the expression given on the right side. This is basically inverse of the integrating factor. We have to take the q, multiply by the integrating factor and then integrate with dt. This C1 is the integration constant. So, we would actually get result saying theta e power integral p dt equal to something on the right side, and then we can take this to the other side and it becomes expression given here. Now, if I take integral p dt can be expanded like this, where I take e power a sin theta or b1 EAC 0 sin omega t. We can write it as a series in modified Bessel function. We have seen this before. It is lengthy, but just stay with me, because the point we want to make is modified Bessel functions will come in the estimation of theta average, and I want you to know how they come. So, we can expand this e power sin theta or a sin theta as I0 of a plus this entire series, all of this multiplied by k1 dc by gamma. This is for the first part. The second part of course remains as k2 by gamma, and integral p dt gives us k2 t by gamma. So, if I integrate this, this gives me k2 t. So, the I0 gives you I0 t, this sin omega t gives you 1 by omega cos omega t, and cos omega t gives you 1 by omega sin omega t. So, I just brought this here, and this is published in 2011 by our group. So, if you wait for a long time and at high frequencies omega tending to infinity, it is possible to show, if you wait for a long time, integral p dt will come like this: k1 dc I0 B1 EAC0 by gamma plus k2, all of this multiplied by t. And when omega tends to infinity, we can say this goes away, this goes away. Under that condition, integral p dt can be approximated by this expression. And therefore, I can write theta with the approximation. I can take this equation, this is precise, and I can approximate that by theta is approximately equal to e power so much. Here of course, q is left as it is. This integral p dt is substituted with the approximation, and this goes away when time is very, very long. It is going to exponentially decrease, and this we do not need to worry. So, we are looking only at the average value. You can show that it is going to be k1 dc I0 B1 EAC0 by gamma, this term. After multiplying this and taking the integration, you are going to get gamma by k1 IDC I0 B1 EAC0 plus k2. Okay. So, the gamma will go away, and you would get an expression saying theta average is k1 dc by k1 dc plus k2, but each one of these k1 dc is multiplied by a what we can think of as a correction factor. Okay. So, normally I would write k1 dc by k1 dc plus k2 as theta ss. When we apply sinusoidal potential, it drifts and oscillates around a new value, which is theta average. In that case, we have to multiply this by I0 B1 EAC0 and this also by I0 B1 EAC0. When EAC0 is small, as x tends to 0, I0 of x tends to 1. So, this will come back towards theta ss, but it will never be equal to theta ss unless EAC0 is exactly 0. Now, this is one example, one mechanism. However, we have tried few mechanisms and we have tried few sets of kinetic parameters. In all these cases, we have found that whenever we replace the k I dc, any rate constant that depends on potential, okay, we correct it with modified Bessel function of 0 order with the corresponding B I EAC 0, it seems to work. So, we call it heuristic because we can't prove it analytically for all cases, but it seems to work, and this analytical expression, at least for the mechanisms we have tried for maybe 4 or 5 mechanisms, and at high frequencies this seems to be valid. So, you can use this to estimate what would be the average value after applying steady periodic condition for a given reaction mechanism and given kinetic parameters.